All right, welcome. I'm Ryan Hoger with the Indiana chapter of Ashrae and Temperature Equipment Corporation, and this week's topic is gas detection systems. All right, so we've got to define a few things before we talk about specific gases. The first definition that we're going to look at is toxicity, right? So this is the ability of a particular gas or fluid to be harmful and poisonous to human beings. Right, so the things that are toxic to materials and metals, we're not talking about that today. For today's purposes, everything we're going to discuss is going to be related to human safety and or human comfort. Right, so that's toxicity, our first definition. A property of more or less poisonous compounds that act as a causative agent in harmful effects on humans. Our next definition is flammability or explosiveness. Right, so this could be a different property of a particular gas. And it is the ability for you to ignite and burn that gas and or explode that gas when it's combined with air and or a spark. And that's me back in my old wrestling days there. But the third definition of a gas that would be something harmful to humans would be deficient, right? Specifically, when we're talking about oxygen in this case, if I don't have sufficient oxygen, then you're going to have difficulty breathing, obviously, and that could have harmful effects on you. And then with other gases, we might also have too much of something. Also, perhaps oxygen. If I have an enriched oxygen environment, that could lead to potential explosivity as well. All right, so those are our main definitions of things that would be harmful to humans. And different gases are going to be of concern to us for different reasons and different applications. How we decide to control these systems, we've got to define for each individual gas. I have to define what my limit is, typically measured in parts per million, of that particular gas and how much of it I can quote-unquote tolerate in a given space, right? So depending on whose data you're looking at, there are typically three different definitions, and all the definitions work the same for the data, whether it's OSHA, NIOSH, or any of these other groups. But sometimes the limit might be different depending on what group you're looking at, and I'll explain that as we go. So the three different potential levels of concern that we have are the TWA, the time-weighted average. This is basically the maximum amount of a gas that you can be exposed to in a quote-unquote regular working environment. So that's defined typically to mean an 8-hour working day or a 40-hour work week. You can't be exposed to more than this level over that time period, right? So in other words, you can have some of this gas in your environment, but you can't have a lot of it because it'll have long-term effects on you. Right? Then we also have a short-term exposure limit, STEL, and right, this is an Ashrae presentation, so everything's got to be boiled down to acronyms, as you guys well know. Right? This is the maximum concentration that someone can be exposed to for a very short period of time. Typically, 15 minutes is that maximum amount of time. Right? So no more than 15 minutes exposure for that particular gas. So basically, when we get to this level, you got to get out of the building. Right? If I'm at the TWA level, that means I need to notify you and I need to make sure that I take measures to reduce that, but you don't have to leave. When I get to the STEL limit, you need to get out of the building, right? It's time to go because you need to get out of there before harmful effects happen. And then we have the ceiling concentration limit, CCL. This is the maximum amount you can be exposed to even for a moment. From the controls perspective, we don't pay any attention to this third value because at that point, it's too late, right? So when I hit the TWA, I want to do some control things to minimize your exposure. I want to turn on exhaust fans. I want to open up ventilation dampers. I want to do things like that. When I get to the STEL, I want to alarm you and tell you to get the hell out, right? When I get to CCL, it doesn't matter. It's already too late from a controls perspective, right? That limit's defined in these standards, but there's nothing I can do from a control standpoint. It's already too late. The first two things didn't work for you. All right, so hopefully that makes sense to everybody. If you guys have questions about stuff, please do type them in, and I will do my best to address them. Address them as they come up. All right. So, for example, if I look at one particular gas, a very common gas that we monitor is carbon monoxide, CO. Right. So, depending on whose standard I look at, whether it's OSHA, NIOSH, or the American Conference of Governmental Industrial Hygienists, which is a mouthful of an acronym, almost as much so as Ashrae. But they didn't get enough vowels in there to make it sound like a word, like we do. Right? So depending on whose standard I look at, I got different answers here. Right? So OSHA says for my maximum, time-weighted average 8-hour exposure, I can have 50 parts per million. So I can be working in some manufacturing plant or whatever, or in some car dealership vehicle bay, and I could be exposed to 50 parts per million over my 8-hour work day, which is a pretty high amount. If I look at NIOSH standard, for the same 8-hour TWA, it says 35 parts per million. And if I look at the hygienist group, it says 25 parts per million. So what am I supposed to do? Which one should I follow? Right? So I get different arguments with different engineers about which ones to follow. As far as I'm concerned, go with the most conservative one in this case, right? Set it for 25 parts per million. If I'm doing some sort of manufacturing plant and there's weird things going on with carbon monoxide, okay, maybe I'll look at one of these other groups and see if it's justifiable to use that. But for most of what we do, which is vehicle spaces, car dealerships, parking garages, boiler rooms, these kind of things that have carbon monoxide, if I have 25 parts per million, something's not right. Something's not working correctly. My exhaust system's broke or my heat exchanger's cracked or something bad has happened. So I don't need to wait till I get to 50 before I freak out. I'm going to freak out at 25, right? So that's kind of the way I look at that in terms of, at least in terms of carbon monoxide. Let's go with the more conservative one, which is 25 parts per million. As we go along today, I will give you different threshold limits for different gases in different applications that we look at. So we'll look at CO2, we'll look at CO, we'll look at battery rooms, we'll look at refrigerant chiller rooms, all that kind of stuff. Try to make this presentation a little bit more practical and a lot less reading codes and standards to you guys. Right, so in commercial buildings, which is the vast majority of the work that a lot of us do, these are some of the things we're concerned about. Now, some of them are very common, right? Like parking garages. I think everybody gets it there. There's cars driving around. If I have an enclosed parking garage, I'm going to have mechanical ventilation systems, exhaust and supply fan systems. Loading docks, which you don't necessarily always think about, but there's lots of trucks that are sitting there with the door open, running their vehicle, pumping fumes into the loading dock. And sometimes that does propagate around the rest of the building. So we do have to be concerned about that as well. Hospitals have tons of stuff going on. There's all kinds of gas detection sensors around there, so we can talk about that. Industrial and manufacturing, we're not going to spend a lot of time on that today because really that becomes down to, well, what are they making there? And depending on what they're making, they should be able to tell me what gases they're off-gassing from their process, and then I can put in sensors and systems to monitor and alarm on those specific gases. So that one's kind of a custom thing, right? The industrial application, what are you doing? Tell me what you're doing in there, and then I can tell you what we got to monitor. Right? The rest of the stuff is more commercial building, and it should be known what we're going to monitor. Commercial kitchens, carbon monoxide is a common thing that we monitor there. And then we have all kinds of recreational things like ice rinks. We typically monitor numerous gases there, right? So I'll monitor typically, most ice rinks I'll monitor 3 different things for 3 different reasons in 3 different portions of the ice rink. So in the spectator area, I'll typically monitor CO2 for occupant ventilation control, and we'll talk about that today. For the ice rink itself, a lot of times I'm going to monitor whatever gas the Zamboni's running on. So if you got a propane-driven Zamboni, I'm going to monitor propane, right? And then typically in a lot of ice rinks, the chiller is an ammonia-based chiller, so I get those low temps. So I'm typically going to have ammonia sensors in the chiller room, right? So lots of things that can be going on in a given facility, just depending on what it is. Right, so why do we even monitor for these gases? Why do we care, right? The main reason we monitor gases in an indoor facility is to protect people, right? If I get to some of these high concentration limits, John's asking about hydrogen for UPS rooms. Yes, we'll talk about that today as well, John. I mainly monitor gases for the protection of people. I want to make sure that I keep things in the safe range, or the safest range possible for these folks. Sometimes we also monitor stuff to protect infrastructure and or the environment, right? So the non-people things, if you will. Right? I don't want to be spewing things out into the atmosphere. We're not going to really talk about much of that today, but there are systems where we need to track different gases that are coming out my stacks and going out to the public world, if you will. I may need to gather data and collect it for different reasons, right? So maybe I'm doing, I don't even know, I'm doing an FDA regulated project where I'm storing pharmaceuticals in a warehouse. And I need to be able to track different things in that warehouse, not just temperature and humidity, but perhaps any types of gases that could have an effect on this thing. All right, so I may be just gathering data, and I don't really have any people to protect, but I want to protect product, if you will, or merchandise. Sometimes I got to do this because it's required by law, right? So certain times, especially in the manufacturing world, I might have to monitor certain gases and be able to report that back to a legal authority. But in other cases, even in a regular commercial building, I might have to have certain sensors in there like carbon dioxide, carbon monoxide, smoke detectors, different things like that that are required by law. Sometimes I'm doing it to improve productivity, which is often the case with CO2 sensors. CO2 sensors, which we'll talk about, are just a measurement stick for how much ventilation air I have. And the amount of ventilation air I have is a struggle between occupant productivity, more ventilation, and energy costs, less ventilation. So I want to make sure I optimize that, and that's where the sensors come in those cases. All right? So we have different types of technologies that we use to sense these gases. These are the three major types. We have catalytic oxidation, we have electrochemical, and we have infrared technology. Right? They all work a little bit differently. I think most people on this webinar probably don't care so much exactly how they work, more as where I'm going to use them in what applications for what reason. One of the things I will mention about some of these, right, so infrared is typically, well, historically has been a little bit more of an expensive sensor. However, it also has a longer life expectancy, right, whereas, let's say, a catalytic oxidation sensor, in order for that sensor to work when it reacts with gases in the atmosphere or in the ambient area, it has to use some of that material in the sensor up in order to read it. So those sensors do decay over time, and you do have to get rid of those kind of sensors. Right, but they're also a little bit less expensive, right? But we have three different technologies. We can use them in different areas, and I'll try to point them out as we go along, which ones may or may not be better for a specific application. So first one up, catalytic oxidation. So this is typically used when we're measuring hydrocarbons, which are, for the most part, things that we can burn and stuff like that, right? So propane, butane, methane. It's very good for those types of gases. We also frequently use it when we're measuring VOCs. Which are present just about everywhere you go, right? The furniture and the carpeting and the paint and everything that you have in your building is off-gassing VOCs for the most part. I do realize that there's a big movement to have low VOC products in buildings, especially with LEED standards and things like that. But we do measure them in some cases. In general, what I would tell you about VOCs is we do not measure them to regulate ventilation control in a space. In fact, I'm not even aware of a ventilation code that allows you to do that. I realize there are manufacturers that promote that, but in general, you cannot use VOCs to modulate the ventilation unless you go under the IAQ procedure of Ashrae, which is a whole other can of worms that you have to deal with. We can use CO2 sensors to regulate ventilation, but you can't just use a VOC sensor because the VOC only measures one type of bad thing. There could be other bad things in your space, right? But anyway, the catalytic oxidation sensors are typically used for these types. They do have a shorter life expectancy, like I had mentioned, because it does break down the material in the sensor every time it reacts with these gases. You can use it for a pretty wide range of gases, right? So it's available in many different types for many different types of gases. And it's pretty good about ignoring the effects of temperature and humidity in regards to its gas sensing ability. The sensors respond quickly, and they're pretty much a linear signal. If I have this breakdown, I can tell you it's this many parts per million, and it kind of follows a nice straight line without any weird curves or anything like that. The next style would be electrochemical sensors. We seem to be using less and less of these. These were fairly popular with things like nitrogen dioxide and carbon monoxide back in the day. A lot of that's switching to infrared technology, but you can still certainly get electrochemical sensors. They are pretty good for accuracy, typically a little bit more accurate than the catalytic oxidation type. And they also have the same benefit of not really being sensitive to temperature and humidity. You do need to get the sensor to be specific to the exact gas that you want. Whereas you can have these catalytic oxidation sensors, you can have one sensor that covers multiple gases, right? There's a pro and con to doing that. The pro is that I can buy one sensor and cover my A, if you will, for 4 or 5 different things, right? The bad news is I can't tell you which thing is the problem in your space, right? So having a more specific sensor, I can say, oh yeah, your problem is carbon monoxide because I'm measuring only for that versus some combination of things. So there's a pro and con to having a sensor that's specific to one gas or broad to multiple gases. In general, I personally prefer ones that are specific to one gas. I know what my problem in my building might be. I want to measure that specific gas and deal with that gas without the effects of other random things. The third type, and my personal favorite type, is infrared technology. So the nice thing about infrared technology, it's extremely accurate. There's lots of improvements that have been made in the past 10, 12, 15 years in terms of accuracy and not needing calibration anymore, and we'll talk about some of that stuff today. It is similar to electrochemical in that I have to do it specific to one gas. I can't get an infrared sensor that senses all refrigerants, for example, right? I have to get one that's for R22, a different one for my R11 stuff, a different one for my 410A stuff, right? So my sensor has to be specific to the gas that I want to measure. It is very common to use these infrared sensors in refrigerant monitoring as well as CO2 sensing technology. Those are the two biggest applications. They do have a long lifespan and are very accurate, and like the other types, they're no longer sensitive to temperature and humidity variations. Right, so all that can be negated out of the sensor. See if you had any questions. Mike asks, regarding accuracy, have you found most manufacturers publish tolerances for the sensors? I'm not sure what you mean by tolerances, but they do publish the accuracy of the sensor. So they'll say, yeah, the sensor is accurate, plus or minus 50 parts per million, that sort of thing. They'll give you that type of data. Some of them will publish it as a percent, but then the percent is more or less meaningful depending on the range of parts per million that you're talking about. But every single sensor manufacturer that I'm aware of publishes data on the accuracy of their particular sensor. All right, let me see here. 1 second. All right, I'm going to launch our first poll question here. That goes up correctly. All right, so our first question is time-weighted average, TWA, means A, maximum exposure over an 8-hour workday or 40-hour work week, B, maximum exposure for 15 minutes, or C, maximum exposure for any amount of time. All right, so if you could, please answer that question by clicking on your choice. And for you guys that need PDHs, you definitely have to answer it. Anybody else is also welcome to answer it because I enjoy seeing your answers and seeing who's paying attention and who's not paying attention. No, I'm just kidding. Actually, I'm not kidding. I do enjoy that. So like 86% of you voted. I'll leave it open for a few more seconds, and we'll see if we can get everybody captured on here. And then while I'm looking at these, why don't you guys go ahead, if you have any more questions at the moment, type them in, and I'll do my best to answer them for you. I'm going to close the poll. Actually, it's 100%, so I'll just close it now. It's the first time I had 100% of the people vote. Indiana people are awesome. All right, let me close the poll. I'll show you the results. 86% of you got the correct answer. The time-weighted average is the maximum exposure for a worker in an 8-hour workday and or a 40-hour week, right? So that's the correct answer. 86% of you got it correct. All right. Syed asks, do they have to be calibrated periodically? So yes and no, Syed, depending on what we're talking about. So depending on the specific gas that we're talking about and the specific sensing technology, you may or may not have to do calibration. As a general rule of thumb, gas detection sensors do need to be calibrated, and as a general rule of thumb, they probably need to be calibrated annually. There are some times you might need to calibrate them more frequently if you have a very specialized process and you have somebody regulating all these gases that you're dealing with and you got to report that stuff. You may be calibrating it more frequently, right? Every 3 or 6 months. In general, though, probably every year, maybe 2. Now, with that being said, some sensors, like CO2 sensors, we'll talk about in a little while, which are being widely used in the commercial applications for demand control ventilation, most of those do not need to be calibrated at all anymore. They all now have, I shouldn't say they all, almost all of them have a routine called automatic calibration. So what they do on those sensors, Syed, is that as long as your building goes unoccupied for at least 4 hours a week, that's enough time for the outside air to leak in and the indoor air to leak out of your building. And basically the CO2 level in your building becomes neutral with the outdoor ambient level. And the outdoor ambient level stays the same all the time. It's the exact same parts per million. It does not change. Right now, over the course of decades, sure, it's been going up, but over the course of hours, weeks, days, years even, it's the same exact number. So if by your area it's 450 parts per million today, that's what it'll be tomorrow and the next day and the next day. So as long as the building goes unoccupied for a certain amount of time, that allows us to neutralize the building with the outdoors, and the sensor can self-calibrate it back to those levels. So every night it can go ahead and do that. Every night it does it again and again and again. So it just constantly recalibrates itself every night. So you don't have to do it on your typical CO2 sensors. You can still get CO2 sensors that don't have that routine, but most of them do. Most of the actual sensors that you buy, they're made in one of two factories to the same kind of spec, with that same automatic calibration. And then sure, those little sensors are shoved in 40 companies' plastic enclosure and punch their logo on it, but the sensors probably all come from the same spot. Generally speaking, two specific factories make a lot of them. Honeywell makes a lot of them, and Telair, which is all, I believe now called General Electric Sensing, GE Sensing, they make a good chunk of them as well. And most people use one of those two sensor engines. Hopefully that answers the question side. All right, let's go back to our slides over here. All right, so there are different types. I'm not going to promote any particular type of manufacturer, and just for the record, so you guys are aware, I don't sell any gas detection sensors. My company that I work for, TEC, does sell CO2 sensors, but we don't deal with other gas detection systems. I just happen to be knowledgeable on this subject, so I like talking about it, but it's not like it's a work thing and we're going to sell you a bunch of sensors. So the fact that I have a specific sensor up here, that's just because it was easy to get their picture. Not that we sell it or anything like that. So a lot of these sensors, depending on what gas you're detecting, come in different flavors. And a lot of times you have a sensor that's just a dumb sensor. He just reads the sensor value and he spits out a signal to somebody else's controller, building automation, whatever, and that controller has to do all the work. Other times the sensor has a controller built into it, like the one I'm showing you here on the right-hand side, right? So that guy has the sensor, he reads it, he compares it to whatever set point you had set on that little screen, and he has the relays and or speed controllers for fans to turn things on and off and change them, right? So you can do it either way. You can get a sensor like I show over here on the left, which is just a dumb sensor, and he reports back to somebody else who makes decisions. Or you can get a sensor built into a controller, and that guy does everything on his own, right? So if I got a little, let's say a car dealership with a little vehicle bay, I probably don't need a full building automation system, so maybe I go with the one on the right where the sensor is built into the controller. He does it all himself. But then my next product I do, maybe I have, I don't even know, a manufacturing plant. I'm measuring 3, 4, 5 different gases, right? So maybe I measure all those gases, I bring them into a BAS that makes all the decisions for me there. So there's a lot of flexibility in what you can do in that regard. Depending on what kind of environment you put these things in, you may need different types of enclosures, right? So you may need ones that are gasketed, water or weather resistant type of thing. So like they're showing you one here at a car wash. I don't know exactly what we're measuring in this type of car wash because it's open on 2 bays, but in any case, if I put a sensor in here, I got to be prepared for the fact that water's going to spray and hit it. Now, hopefully the dude's not using my sensor as his target to spray it on purpose, but whatever's bouncing off his car might be hitting my sensor. So I need to think about that. Where am I going to put this sensor, and does it need to have any type of water-resistant type of enclosure and things like that? Now, if I need to put it in an environment that's readily going to be getting wet or chemicals that are caustic to the materials that are going to be in there and stuff like that, I don't have to put the sensor in the actual space I care about. I can put the sensor back in some control room, if you will, or a closet or whatever I got, and I can run pneumatic tubes out to the space. And there's a little fan that I put next to my sensor that basically draws sample air from the space through the tube so I can test that particular air. There's a little bit of a delay lag, as you would expect, for that gas to travel down the tube and make its way to my sensor, but it does protect my sensor. Sometimes if you have lots of spaces to monitor as well, you can use those sample draw type systems to have one sensor monitoring multiple spaces, and he'll, for a couple minutes he'll monitor channel 1, then a couple minutes channel 2, and then 3, and then he'll rotate back around. So depending on your application, how critical it is, you can do stuff like that. But generally the reason to use a sample draw system is because I don't want the sensor in the space for some reason, right? Because something bad's going to happen if it gets wet, or because someone's going to hit it with something or whatever. The type of sensors that are available from manufacturers, vary widely in terms of what you can do with them. Like I said, sometimes the sensor has its own controller built in, and it basically has its relays that it turns on. And it turns on relay 1 to turn on exhaust fan 1, and relay 2 goes for exhaust fan 2. It's all self-contained and it's beautiful and everybody loves it. Other times I may want to just get the sensor value reading and send it to somebody else, to my building automation system. So a very historical common way that we've done that over time is with a 4 to 20 milliamp signal. sometimes also expressed as a 2 to 10 volt DC signal. In either case, my sensor reads a value, and let's say my sensor, for sake of argument right now, is a CO2 sensor, and it can read 0 to 2,000 parts per million. I can correlate 0 parts per million to 4 milliamps. I can correlate the 2,000 parts per million to 20 milliamps, and then I can send that signal to my controller, and he knows anything in between, right? It's just straight linear. So if I said, oh, you got 12 milliamps, he'd say, oh, 12 milliamps, that's halfway between 4 and 20. Oh, okay, you have 1,000 parts per million. Great, now I'll make my decisions based on that value. Right? That's a very common way for not only gas detection sensors, but humidity sensors and all kinds of stuff we use in HVAC. In more recent years, there's been a movement to have the sensors communicating on a network with the actual controllers, right? So there's ways we can do that. BACnet, as you guys probably know, which is an Ashrae Standard, is a common way to do that. LAN, Modbus, and a few other niche things as well. So that way the sensor can send his data over a communication cable back to a controller and tell him his data that way. And sometimes I can get more data that way. Other stuff that you can do on some of these actual sensors, and then we'll start talking about some of the applications. Sometimes the sensors, when they are expelled, if you will, right, because they don't last forever, especially if they're catalytic oxidation type, right, I have to replace them. Sometimes you got to replace the whole thing. Other times, like the one I'm showing you here, I could pull that sensor cartridge out and just replace the sensor, but the controller box can stay in its place with all of its wiring and relays and set points already still there. I just swap out the sensor. Other types can be calibrated, but when they have to be replaced, they got to be replaced. So for example, even the carbon monoxide sensor at your house does not last forever, right? In general, the recommendation for residential carbon monoxide sensors at your house, I should have put this as a poll question just to see what you guys all thought, right? But it's generally 5 years. Sometimes you'll see sensors that say 7, but generally 5 years, and it's no longer any good. Most of us go look at our carbon monoxide sensors. We probably had them for 10, 12, 15 years. Throw them away. They don't do anything anymore, right? They are useless. And the sad thing about that residential world is they used to make them so they alarmed when they were no good anymore. Now a lot of them don't do that because it causes nuisance trips that people didn't like or would notify fire departments and stuff like that. So they kind of disabled that feature, and you have to just know every 5 years I got to get a new one. I know most of you don't do that. I didn't used to do that until 10 years ago either. And I finally learned that fact. Now every 5 years, I got it on my calendar. I literally go yank all my carbon monoxide sensors out, and I put new ones in. Yeah, it's expensive. It costs me, $200 every 5 years to buy a bunch of sensors. So what? $200 is nothing in the grand scheme of it, right? In any case, that's my sidebar discussion. You can mount these on the wall, which is very typical. In HVAC applications, we sometimes mount them in ducts. Typically, we do that with an aspirator box. It's the same sensor you'd put on the wall, but we put in a box like we're showing here on the right-hand side, right? And then we have tubes that go out into the duct and come back. So I can draw a little bit of air in from the duct and put a little bit of air back in the duct. I get a little circulative pattern happening so I can sense air inside my aspirator box. Depending on the application, you may want to measure stuff in the duct. In general, as a rule of thumb, you want to measure stuff in the space because that's where the people actually are. Measuring the duct is a second choice if I can't put it in the space because there's a problem, hose, spray, water, whatever, that kind of thing. Sometimes you may need to alarm people. Sometimes you may need to alarm a BAS, and that's fine depending on what it is. Other times, if it's a hazardous type of gas, I need to alarm the occupants. And depending on what I'm doing and what the standards and codes are, I may need to notify them visually and audibly. So strobe lights, and horns are common accessories that you can get and add on to these systems as well. Sometimes you can have communicating gas detection systems like I'm showing you here, where the sensors can communicate back to the main panel, and that can communicate to your BAS, and it can even communicate to your strobes and stuff like that. That's not super common. Usually we have one sensor with one strobe and that kind of thing, but if you have a large system with lots of stuff going on, you may want to choose this type of thing. Right, and here we got all kinds of mix of stuff. We got sensors that go in space, we got sample draw systems that have the pneumatic tubes, we got enunciation panels, all kinds of things. All right, so some of the specific gases. CO2, carbon dioxide, hopefully you guys are all aware of that. Carbon dioxide is not a poisonous deadly gas. It is frequently confused with carbon monoxide with an M, so CO versus CO2. Right now we're talking about CO2. It is a totally normal thing. You exhale it as a human being. You suck oxygen in. You exhale CO2. It is not harmful to people until you get to insanely high concentrations. typically, depending on who you're talking to, 30 or 50,000 parts per million. You can't get up to 30,000 parts per million in an office building or school or anything like that. It's literally impossible. There's way too much leakage. You have to put 1,000 people in a 10 by 10 room to try to get that high. I've tested this, right? So when we're talking about normal levels, we're talking about 800 parts per million, 1,200, 1,500 parts per million. Those are all safe levels. So the reason we monitor CO2 is not because it's because of a safety issue. The reason we monitor CO2 is as a surrogate to count the number of people breathing in a room. And if I know how many of you are in there breathing, I can decide how much ventilation air I need to bring in for safety and code and all that good stuff. So we'll talk more about that application as we go. But CO2 is an extremely common gas monitored, and perhaps arguably in commercial buildings, the most common thing that we would have sensors for. Carbon monoxide is obviously similar to CO2 in terms of its makeup, but I have that one less oxygen atom, so it's a totally different gas. Carbon monoxide is an odorless, colorless, deadly gas, right? If you breathe it in large concentrations or in small concentrations over a long time period, it can poison you and can cause serious health problems, perhaps even death, right? So totally different argument. Generally speaking, it is a product of incomplete combustion, right? So if I don't have complete combustion, I got a crack in my furnace heat exchanger or something like that, that's when I'm going to have carbon monoxide issues. Anytime you have a gas burning appliance, somewhere in a residential or commercial building, you should have at least one carbon monoxide sensor, perhaps even more. Residentially, you're required to have one near the appliance, your furnace, for example, and you're also required to have one on each floor of living space. So if you got a two-story house, you need to have one upstairs, one downstairs, and one in the basement, right, near your furnace, that sort of thing. For our purposes, we're going to use 25 parts per million as our maximum limit. I realize some of the other organizations said 35 and 50. I'm going to go with the conservative one, which is 25. Right? If I got 25, something bad's happening, and I should be taking precautions. Nitrogen dioxide is another very common one that we measure, NO2. This is oftentimes measured as when we have diesel vehicles. Mike's typing in a question, could you restate the requirement? I'm assuming you're talking about the CO requirement residentially that I just mentioned. In a residential house, you need to have a carbon monoxide detector near the combustion appliance in the same room as your furnace and or water heater. And then you also need to have a CO sensor on each floor of living space. So I'm talking about single family houses here in that example. So each floor you have a CO sensor, plus you have to have one in the same room as the furnace. Right? Sometimes you get the CO sensor combined with the smoke detector, and that's fine. You can do that. And then also smoke detector, you need to have a smoke detector not only in those same spaces that I just mentioned, plus you have to have the smoke detector in every single bedroom as well. Right? So that's all part of, you're asking about Indiana, Michael. That's all. What I'm talking about here is national standards, right? So I don't know if Indiana specifically calls out national standards, but even if it doesn't, you should be following the national standards, because if not, you'll be the one that either as a homeowner dies or as an engineer gets sued. All right, so NO2, nitrogen dioxide, typically we're measuring this as a product of diesel engine combustion. So we'll use this in vehicle spaces that have diesels, right? So bus terminals, train terminals, sometimes parking garages, but not always. Loading docks for sure, that kind of thing. It has similar effects on your body as carbon monoxide in terms of making you sick and having problems. It is not exactly the same effect, but it is similar in terms of affecting your breathing ability. It's also something that you wouldn't you wouldn't have from another type of system. It's typically going to be a diesel type thing. We measure oxygen frequently, O2. We don't measure oxygen necessarily because we don't want it. We want to make sure you have enough of it. So in general, we measure this in spaces where oxygen is being consumed. So if I have a process going on that's using the oxygen from the space, I want to babysit that space to make sure that I have enough oxygen for the occupants, right? So we're talking about here in terms of welding stations, industrial production, stuff like that. We also put oxygen sensors a lot in fire stations. Because fire stations store oxygen tanks. And in those cases, I want to measure the oxygen because I want to measure to see if there's too much oxygen, because that means some of my tanks are leaking. And if I leak a lot of oxygen, it's more likely that I can have a combustion incident, Now, hopefully in a fire department it doesn't happen because those guys all should be smart enough not to be smoking by the oxygen tank, right? But that doesn't mean we don't want the belt and suspender sensors. In fact, you'll find in fire stations, the more sensors you give those guys, the happier they are. They want to over monitor everything because that's just the way they're wired. But we can monitor oxygen for too little or too much depending on our concern. Regardless of what type of gas sensor we're working with, whether it's one of the ones I just mentioned or some of the ones I'm going to mention in a little bit, like hydrogen or refrigerants and stuff like that, I got to decide, is this gas lighter or heavier than air, right? Why do I need to know that? Well, I need to know that because I need to know if I want the sensor at the floor or if I want the sensor up towards the ceiling or I want it in the breathing zone, if you will, 4 to 6 feet off the ground, right? If it's about the same weight as air, I want the sensor in the breathing zone, 4 to 6 feet off the ground because I'm trying to protect people, and that's going to give me the first notification of that. If my gas is heavier than air, I want my sensor at the ground because the gas is going to pool at the ground, so I might as well find it down there first instead of waiting until it gets higher up, right? And then if it's lighter than air, I'll measure up at the top of the ceiling, right? So you'll see some of the specs I'm going to show you here. It'll say measure 1 foot off the floor or 1 foot below the ceiling, right? Or measure it at the breathing zone level because it just depends on whether the gas is heavier or lighter than air. And I want to detect it in the first place that I can likely find it, so I can do something about it sooner rather than later. So depending on what I'm doing, right now I'm showing you carbon monoxide and nitrogen dioxide. And the example that we're showing you there is a parking garage facility, which is a very common place to have gas detection systems. Generally speaking, I can cover about a 50-foot radius of detection, right, which is pretty substantial if you think about it. And I can think about that requirement and decide how I'm going to lay out my sensors for this parking garage on the different levels and so forth to get the maximum amount of coverage, right? Carbon monoxide, carbon dioxide, and nitrogen dioxide all are similar in that they want to spread equally far apart from each other. So if I got a bunch of them in a group, the little molecules want to get equally far apart away from each other. So they will spread across the space fairly rapidly. And then in the case of carbon monoxide and carbon dioxide, they are close to the same weight as air. So I want to measure those ones in the breathing zone. All right, here gives you some relative densities of some of these things. So you can see carbon monoxide is 0.968 as relative to air, which is 1.0, right? So carbon monoxide, I want to measure in the breathing zone, you know, that 3, 4, 5, 6 feet above the floor type of thing. If I look at oxygen, relatively speaking, it is similar to air as well. If I look at some of the other ones, like nitrogen dioxide, when it's cold, it is heavier, right? So I want to measure that. Well, this slide's a little bit confusing because we have the cold here, but I didn't put the hot one on here. When nitrogen dioxide is hot, like coming out of a diesel engine, it actually rises quickly and it's quote unquote lighter than air. So we typically measure nitrogen dioxide below the ceiling level. That's why they're telling you that here on the right. I should have had 2 rows on here, one for cold and one for hot nitrogen dioxide. So I do apologize for that. There's a note on the bottom there, but I realize no one's going to read the note. Hot NO2 gas from exhaust systems is lighter than ambient air. Right? So normally we're measuring it above the ceiling, which is why it says that. In larger facilities like a parking garage, you can zone these systems out, just like you could a temperature control system, zone system, if you will. Or I can have different sensors on the different levels of the garage, spaced apart so I can get decent coverage. And then those can all report back to multiple or singular ventilation systems. I can have a staged ventilation system, or I can be ramping up a VFD. Nowadays, ramping a VFD is more common, right? The more CO I have in the parking garage, the faster I speed up the exhaust fan, which moves more air through the whole building assembly, which clears the CO out faster. And then as cars are not driving around, the CO level goes down, I slow down the ventilation fan, right? If I don't do this, my other choice is to run the ventilation fan 24/7, which is extremely expensive, right? But if I know vehicles aren't driving very much right now, and I have less CO in the air, I can slow my fans down, right? So in the morning when everybody comes to work, yeah, I got to ramp them up a lot. But then when they're all at work, I can ramp them down lower because there's hardly any vehicles driving around. You can use these things in a standalone configuration, or you can use them with remote sensors. This is very common when I want to do CO and nitrogen dioxide in the same parking garage, right? I can measure CO at the main controller on the wall and have a remote NO2 sensor up near the ceiling where the diesel gas is likely to accumulate. So I can have one controller, if you will, with 2 sensors on it, controlling a single exhaust fan. I can also have network systems using BACnet or other types of communication, and there's even wireless systems as well now. So some of the manufacturers have wireless systems, which is useful from an installation cost standpoint. The only negative really is I got to go around and change batteries because there's no continuous power available, but that's not the end of the world. And sometimes you can hardwire them to a power source. So maybe I can get a power source, but I can't get a communication source. So that does come up sometimes as well. Typically, these are self-healing mesh networks, so if somebody gets knocked off the wall by a car, the sensors will find a new pathway to talk to themselves. If one of them goes into alarm, he'll report it back to the main panel, and they'll use that mesh network, if you will, to report it to the alarm relay panel that will start turning on exhaust fans or strobe lights or whatever I got going on. And hopefully that your exhaust fan does not look like that. Skip a little bit of the wireless sensors here. These are common applications that we like to look at: garages, schools, loading docks, warehouses, bus terminals, train terminals, fire departments for sure, hospitals, kitchens, vehicle repair shops, golf courses where they got the golf carts stored, passageways, tunnels, that sort of thing are very common in addition to the manufacturing sector. Right, so I'm going to go through one slide here on each of the major applications that you'd have for commercial grade gas detection. First one being indoor parking garages, which you mentioned a couple times already. You definitely want to measure carbon monoxide. That's the vehicles that you're going to be measuring. You may also want to measure nitrogen dioxide if you're going to expect a lot of diesel vehicles. A normal parking garage does not have a lot of diesel vehicles, so typically you don't need to measure that. But if for some reason you were expecting that, you're doing a parking garage in Europe and diesel cars are common, okay, different rules. Or you're doing a parking garage somewhere where you're expecting a lot of pickup trucks and dualies and all that, okay, maybe you need to do it as well. For carbon monoxide, our typical TWA, right, my 8-hour maximum is 25 parts per million. So when I get to 25 parts per million, at that point in time, I want to do something with the ventilation system. Either turn more exhaust fans on or ramp my exhaust fan up, that sort of thing. If I get to the STEL, right, and that was my second threshold, that's the maximum I can be exposed to for 15 minutes. In this case, for carbon monoxide, it's 200 parts per million. If I get to that level, I want to turn on my oh crap alarm, right? I want strobes going on. I want horns sounding. I want you to get the heck out of this facility. I want to scare you out of this building, right? So that means that my control system for my exhaust fan did not do a good job. The fan's broken or whatever, and I could not maintain the 25 parts per million. The sensor values continue to climb. I get to 200. I alarm it. I tell you to get the hell out of there. Right? Nitrogen dioxide, if I have diesel vehicles, the thresholds are much, much lower. Right? 0.7 parts per million is typically my control point. I want to keep it below that, so I will turn exhaust fans on to maintain something less than 0.7. And if I get to 2 parts per million, I will alarm it and tell you to get out of the building. I typically measure that below the ceiling in terms of a vehicle scenario for nitrogen dioxide, because when it's hot, like it's coming out of the exhaust stack of your truck at 1500 degrees, it's going to be very hot. It's going to rise up towards the ceiling. So I'm going to measure it up there. And both these sensor types typically handle a 50-foot radius of detection. When you look at different manufacturer specs, they will all have similar technologies, but yet they'll all have different radiuses of detection. This one will say 50, this will say 25, that one will say 70, right? It's all based on what they feel a good amount of time delay is in order for that gas to make its way to the sensor. I'm just giving you a very common default number here. Depending on how your parking garage is laid out, you got to think of where all these sensors might go, whether you want to use wired or wireless, and if I can get decent coverage that way. Commercial kitchens are another example of where we want to monitor stuff. Generally, what we're monitoring in a commercial kitchen is carbon monoxide. For some reason, if the exhaust systems weren't working properly, I would like to be able to sense that. Obviously, I don't put the sensor very close to the grill. I want it on the other side of the room. So that way it doesn't get false alarms and things like that. I may have other sensors in the application. I may have CO2 sensors in the dining room area. I could potentially have refrigerant monitoring sensors in the refrigerated area, but that's not very common. I typically don't have a large amount of refrigerant involved, so I typically don't do that, but you could do that kind of thing. Move along here a little bit. So in terms of parking garages, the savings can be quite substantial by stop running your fans max capacity 24/7. So anywhere you have vehicles, this is a pretty good potential. Parking garages, loading docks, bus terminals, car dealerships, fire stations, all excellent candidates. By the way, a fire station needs CO and you need nitrogen dioxide because you have both types of engines running in there. There are tools available from the different manufacturers to help you calculate savings. and it can be pretty substantial. For example, this parking garage was costing $9,700 in fan energy a year. After retrofitting sensors, they're estimating $1,100. It's quite a bit of savings just for that one fan, and there's 2 identical fans in there. There's lots of studies out there that kind of support this stuff as well. And pretty much anything you want to promote to someone, you can always find a study to back it up, right? So I'm not going to get too excited about this. But in this example, for this large parking garage, they had a payback of 9 months, saving a huge amount of money, $200,000, but it's a massive parking garage, so I get it. All right, next scenario, chiller rooms we'll talk about, right? So for a chiller room, I have to know what refrigerant you have, and I have to buy a sensor specific to that refrigerant. It is possible to get refrigerant sensors that detect multiple refrigerants, but generally these are not going to be the more robust, higher reliable infrared ones. They're going to be the ones that break down over time and you got to replace. So I would recommend you use the infrared sensors, and I'd recommend you get a sensor specific to each refrigerant that you have. In most cases, your chiller room only has one refrigerant type, so it's not a big deal. Sure, every once in a while you'll have an R11 machine sitting next to an R134A machine. If that's your rare scenario, because you didn't replace both chillers, you only replaced one chiller, fine, buy 2 sensors. Do it the right way. Depending on which refrigerant you have, there are different threshold limits that are established. Most of the refrigerants that we deal with in a chiller room, which nowadays is pretty much 134A, they have 250 parts per million as the TWA, the 8-hour maximum. So I want to use my control system to keep the refrigerant below 250 parts per million. That means if I start getting close to that, I want to turn on exhaust fans, right? And I also want to alarm the building automation system so the operator knows, hey, I have refrigerant in that room. Something's not quite right in there, right? You need to go look at it. If I get to 500 parts per million, then I want to go into alarm. That means that I sound the horn, I turn the strobe lights on, and I basically indicate to people to get the hell out of there, right? The sensors are typically located 1 foot above the floor because refrigerant is more dense than air, so it will fall to the floor. And typically we can handle a 20-foot radius of detection, which usually means 1 sensor per chiller. Sometimes I can get away with 1 for 2 chillers if I put it right between them and the chillers are close, but usually 1 per chiller. And then for all you fans of a particular brand of chiller, you should just note that not only is R123 on a phase-out schedule, it also has a much lower threshold for safety here. So just keep that in mind. I won't pick on any names because it's an Ashrae presentation. Ashrae Standard 15 is what governs most building codes for chiller room concerns. I got the 2007 version up on here. I believe the newer one has the exact same language, so I didn't bother changing it. Plus, most of your codes are still following old standards anyway. But basically, when you read through the Ashrae standard, it's basically going to tell you that you need to have a sensor for each refrigerant that you're expecting to have in that room, right? So you need a 134A, you need a R11 if you have that, those kind of things. You have to locate it near the equipment so you can sense it properly. You have to control it to the recommended TWA for that particular refrigerant. You have to have visual and audible alarms inside the chiller room and outside every single entrance to the chiller room so nobody goes in there when there's a problem, right? So that's the main catch on that. If you look at the City of Chicago code, which a lot of you guys do projects in, there are very similar rules. I got to have visual and audible alarms both inside the room for people that are working in there and outside every single entrance to the room. Additionally, in Chicago, you got to provide scuba gear, right? So that's basically the face mask and tank. That way somebody can go in there and help rescue somebody else. In Chicago, you're required to have 2 tanks ready for 30 minutes each. It's not for me to go in there and hang out and try to work on stuff in there. It's for me to put the tank on, go in there, rescue my buddy, drag him out, right, and then open up the doors, make sure the fans are on, and try to ventilate this space out, and then go work on this thing later on. All right, so those are my main rules. Both Ashrae and City of Chicago pretty much saying the same thing for gas detection portion of it. This is what a particular mechanical room might look like. Let me see if I can get my little pen thing going here. Right, so over here I have a R22 chiller on the bottom right, so here's a sensor for him. Right, I have several 123 chillers, so there's a sensor there, a sensor there, a sensor there. Pretty much one for everyone. It's possible, depending on this distance between these 2 chillers right here, I might have been able to put 1 sensor in and cover both of these guys. But just from a general practice standpoint, it's easier just to put 1 in for every chiller and be done with it. Plus, that way, when they change 1 chiller out and it's a different refrigerant type, It's not some weird thing. It's like, oh, I just need to change the sensor out. I don't have to rewire stuff and run more conduit and try to figure out what the rules are. It's just done. One sensor per chiller is the way to go. I have inside the room, I have an enunciation panel. In this particular case, there's both a horn and a strobe light built in that panel. It's fine if you have them separate. You can have the panel turning on a relay, and the relay can be turning on, the little light bulb. Look how good of an artist I am, right? Turning on my light bulb and sounding my horn separately, that's fine. But I have to have the light, the strobe light, and I have to have the horn. Additionally, outside every door to the room, whether it goes into another mechanical room, to a hallway, or to the exterior outdoors, I have to have some way to have a strobe light and a horn out there. I don't have to have a panel necessarily, but I got to have a strobe light and I got to have a horn at the very minimum. That way no one goes into the room unexpectedly. All right, so that's my Ashrae standard, if you will. Oops, let me clear that other stuff off the screen. And let me go ahead and launch poll question number 2 real quick. What gases should be monitored for parking garages? Right? Oops. A is CO, B, CO2, C, NO2, D, none of the above, or E, both A and C, which would be carbon monoxide and nitrogen dioxide. I guess depending on your specific parking garage, there could be 2 potentially right answers. Give that to you as a hint. Look at the questions. There's no new questions being typed in. Looks like 95% of you voted. 96. So I'm going to go ahead and close the poll. If anybody hasn't voted yet, please do so. In 5, 4, 3, 2, 1. All right. Looks like most of you got the correct answer, which is both A and C. If you just said A, that would be okay as well. Most parking garages just have gasoline vehicles, and carbon monoxide, CO, is what you would detect. If I have diesel, I would also have NO2. So the answer I was looking for was E, which is both A and C. But if you answered just A, that's fine also, because that's the normal parking garage. If you answered B, CO2, then you are flat out wrong. We would not measure CO2 in a parking garage. CO2 is for people measurement, not vehicle measurement. And then obviously D, none of the above, is wrong as well. All right, let's keep on moving so we can get everything wrapped up here. If I have multiple stuff going on, I don't necessarily have to have multiple control systems, right? I can have one control system measuring multiple things. Now, in general, I'm not going to have the chiller and the boiler in the same room, right? But I might have them on the same control system, if you will. In this case, I'm monitoring 3 refrigerant sensors for chillers. I'm also measuring sensors for the boiler, which is probably a carbon monoxide sensor or a methane sensor, depending on what this boiler is doing. And it could all be going to one control panel that's doing all my fans and alarms and horns for me. So I could network these things together if I want to. In a boiler room, the things that I'm most likely to monitor, carbon monoxide is the most common. We already mentioned the thresholds for that, so I might want to measure that in my boiler room. And then I may also be concerned with measuring methane in there, depending on what my boiler is doing. So I may measure that. But in general, carbon monoxide, which you'll see in most boiler rooms. Methane is typically lighter than air, so it's going to rise up to the ceiling, so I want to measure that one at the ceiling. Carbon monoxide is approximately the same weight as air, so I'll measure that at the breathing zone limit, 5 feet above the floor approximately. If I have a swimming pool, obviously I want to measure chlorine. Specifically, I want to measure it in the mechanical room, not necessarily the pool room itself, but the mechanical room. There's several different stories out there. You can Google them if you want to about young teenagers that are doing the pool chemical stuff for their high school or for their local pool or whatever, the YMCA. And there's 2 different stories out there you can find where these young kids actually died in the room because the chlorine was so strong in there. It can be a pretty dangerous thing. The thresholds, as you can see, are very low amounts. Half a part per million is basically when I'm going to start my control sequence and turn on exhaust fans. If I get to 1 part per million, that's when I'm alarming. Horns are going, strobes are going, that kind of thing. Chlorine is heavier than air, so I measure it down by the floor level, about 1 foot above the floor. Battery rooms, someone had asked about that earlier. If I have battery storage or if I have a golf course where they have electric golf carts and they're all stored in one, one garage together. The sensor that I would like to use for that is hydrogen, and the threshold works a little bit different. We don't measure that in parts per million. We measure that in percentage, but basically there's a similar kind of goal. If I am getting close to 1%, I want to turn the exhaust fan system on. As I get over to 2%, I need to alarm you to tell you to get out. 2% in the hydrogen is basically 50% of the dangerous deadly level. So that's why we're telling you to get out at that point. Hydrogen, as you well would expect, hydrogen balloons and all that, it's lighter than air, so we measure it up at the ceiling level. About 20-foot radius of detection per sensor. There's lots of stuff going on at wastewater treatment plants, but these are some of the common things I might want to measure there. And one thing I'll mention about the wastewater treatment plants, typically everything that you put in there has to be explosion proof. So you can't just put regular sensors in most of the spaces. You typically will have to use an explosion proof sensor in the actual space. So just keep that in mind. A little bit different thing going on there, which means a little bit higher cost for the sensors, but there's lots of stuff going on. So methane is a common one that we would measure. Hydrogen sulfide, which is that stinky egg odor or whatever you want to call it, is another one. That guy has a 5 part per million threshold. I want to control it below that. If I get to 10, I want to alarm. Hydrogen sulfide is heavier than air, so I measure it down at the floor. And then I typically want to measure oxygen to make sure I don't have too little or too much going on in there. So there's lots of work to be done in a wastewater treatment plant if you're into gas detection. MRI rooms are a really common one as well. In these rooms, we got to measure for lack of oxygen in there. So it's a very common sensor. I don't know if it's a code required thing or if it's just a standard good practice that everybody that runs an MRI room does. But every one of them I've ever done has an oxygen sensor in there. Oxygen, we measure above the floor. It's a little bit heavier than just plain air because, as you know, plain air has other things in it. We want to make sure that we don't have too little oxygen in most of these cases. Now, one of the things about MRI rooms is they don't want any metal stuff in the room, as you probably are aware. So on these systems, I have to use a sample draw type system, which we're showing you up there on the left-hand side. So that goes back. So if you've ever been in an MRI room, right, the technician gets you all set up, slides you into the tube, then they go behind the lead wall and they run the machine from behind the lead wall, right, because they don't want to be exposed to this thing all the time, right? You're just there one day. They're there every day, every hour. This panel would go back in that same room with that guy behind the lead wall and all that. So all the metal components are behind that lead wall. These are the actual 2 sensors in this particular case. And I don't know if you can see it over here on the left side, but they have these blue tubes that would go out into the actual space, right? And it'd sample air from the space. That way there'd be a small fan that would draw air through the tubes, and I'd be able to measure the gases in that room that way. In this case, the gas would be oxygen. If you got a brewery job, and hopefully you got a brewery job because it's literally the best project you could ever do because you always get free beer, and that makes it awesome. There's 2 things we typically want to monitor in those spaces. Typically, a lot of breweries have ammonia-based chillers, just because ammonia is, I guess, a little more friendly than refrigerant if something were to happen in the food industry, if something bad happened. So you typically got an ammonia sensor that you have to get. Ammonia is NH3. Our threshold, whether it's a brewery or whether it's an ammonia chiller in an ice rink or whatever, my threshold is 25 parts per million I want to control to. That means my exhaust fans kick on, and I try to keep it below 25 parts per million. I still notify the BAS if I have one. If I get to 35 parts per million, that's when the strobes and horns go off. Ammonia is typically lighter than air, so I will measure it up at the ceiling, and I get about a 20-foot radius of detection. Also, I want to measure carbon dioxide in a brewery because, as you can imagine, we're carbonating the beverage, and carbonation, if you weren't aware, is carbon dioxide, right? So I have carbon dioxide on hand and available there. I need to regulate to make sure I don't get out of whack with that. Now, previously I said carbon dioxide was not dangerous, right? But I was also talking about small levels like you'd find in an office building. Here I want to know if something's out of control. If I have 10,000 parts per million, obviously I have some kind of leak and something's not right. So I need to deal with that. So typically we control that below 5,000 parts per million and we alarm it at 15,000 parts per million. Carbon dioxide is about the same weight as air, so we measure it at the breathing zone level. Arenas I mentioned before, we got ammonia chillers in most cases, so I want to have that ammonia sensor in the chiller room. I want carbon dioxide in the spectator arena for the purposes of ventilation control. You'll notice with carbon dioxide, though, we do not have a 15-minute maximum exposure because it is not considered a harmful category of gas. right? I'm controlling it for ventilation reasons, not for safety reasons, right? We're showing 850 parts per million as a control point on here. Typically, we have a linear control ramping scale that goes with the outside ventilation damper. So I'll typically be ramping the ventilation between, say, 600 parts per million and 1100 parts per million. So 850 we put on the screen here just as a number to put up there. It's kind of a gauge figure in your head. I might have carbon monoxide, depending on what kind of Zamboni I am driving, or I might have propane, depending on what kind of Zamboni I am driving, right? Look at John. John types in "Go Wings." Nice. I don't know if that's a question or a comment, John, but nice. Would also prefer the Blackhawks. If you could type that back in, that would be better, John. For human ventilation, typically I'm looking at carbon dioxide. As I mentioned, carbon dioxide is not a deadly thing. It is just something I want to use as a surrogate to see if there's people in the room or not. If there's not people in the room, or there's less people in the room below the code design number of people, I can modulate your ventilation air back. If your space required 1,000 CFM of outside air and less people show up to work today, I can throttle your ventilation air back if I can use CO2 to measure the amount of people that are in there. This is allowed by Ashrae Standard 62. It's in the International Mechanical Code. It's actually even required by most of the energy codes. I could talk on that topic for an hour and a half. We won't do that today. If you want to learn more about CO2-based demand control ventilation, I have several recorded webinars I can send you the link to, and you can learn about it that way. I am showing a limit up here of 5,000 parts per million. That's not because something bad is going to happen and you're going to die. It's just that if I get to higher numbers up there, that probably means either there's something wrong with my sensor or I got some sort of problem that I need to deal with from the BAS standpoint, so I do want to alarm you. All right, sometimes there's rebates for some of this stuff. Like CO2, there's a standard rebate because, like I said, you can cut back the ventilation air, which saves you energy. So depending on where you're at in the Midwest, there's probably free money available for you. So specifically today, we've got a lot of people from Indiana on the webinar. NIPSCO has a rebate of 15 cents per square foot if you put CO2-based demand control ventilation in. On the electric side in Illinois, ComEd has a rebate of 4 cents per square foot. On the gas side in Illinois, you'd have to do it as a custom. And then Michigan has rebates, Wisconsin has rebates. So all you guys that I see on the webinar from different states, you probably have rebates there that are available to you. Lewis is asking if NIPSCO is for commercial projects. Yes, everything on this screen is for commercial. There are no rebates residentially for CO2 demand control ventilation because you cannot use CO2 demand ventilation residentially. You typically have a very large volume of indoor space relative to a low number of occupants, so you cannot use CO2 in those kinds of spaces residentially. CO2 control is only for commercial applications, and it works best when you have spaces that have lots of outside air requirements and have lots of people coming and going. So think movie theater, dining room, classroom, lots of people, and they come and go. That's when DCV makes the most sense. But yes, all these rebates are residentially orientated. Let me launch the last poll question here. Carbon dioxide, CO2, is hazardous to humans. True or false? So 95% of you voted. I'll give it a few more seconds for the last stragglers. And then I'll close this poll in 5, 4, 3, 2, 1. All right, so most of you got the correct answer is false. CO2 is not hazardous to humans. There are no published levels by any cognizant authority stating that a certain level of CO2 is harmful to humans. And as I mentioned, CO2 is something you exhale yourself. You make the CO2, so obviously it's not harmful to you. Now, actually, Tom wrote in, Ryan, depends on the level, right, extreme. So Tom does have a good point. If I get to really high levels of CO2, like 30,000 parts per million, yes, it can be harmful. But it's not so much because the CO2 is harmful to me. It's because at that point I've displaced so much oxygen that I can't breathe oxygen, right? So the CO2 itself isn't really harmful in and of itself. But if I have so much of it, I've displaced the oxygen that I need, that could be problematic. But in general, the answer we're looking for here is no, it is not harmful. All right, so that kind of concludes our webinar. If anybody has more questions, please do type them in. I will stay online for a few more minutes and try to answer them. And actually, I just noticed I have my old email address on there. So let me just change that real quick. If you want to email me a question later on, that's totally cool. I don't have any problem with that. There, that should be my correct address now. I have my old address up there from when I used to be involved in gas detection. But you're still welcome to email me a question at ryan.holger@tecmungo.com. I do thank you guys for joining us on the webinar today. Like I said, this is our second Indiana Ashrae Chapter webinar. So far, they've both gone pretty good, and some folks were able to get some PDHs as well as doing a little bit of learning. So we're all for that. If you have topics that you want to do in the future, see us do as a chapter, please do send them in to Lewis, and then you can evaluate those to see if they're ones that we can get done. Whether it's me or somebody else in the chapter that's doing it, doesn't really matter to me. But if there's topics you guys want to hear about, let us know, and we'll try to set those up in the spring or whenever. And then Lewis is reminding me to mention that we do have a chapter meeting coming up in 2 weeks. He's reminding me that, but I don't have it memorized on exactly what date that is. So I will look it up unless Lewis types it in faster than I can look it up. November 20th is our chapter meeting. So we have our usual South Bend meeting at lunchtime and our Northwestern Indiana meeting in the evening. So November 20th, if you didn't see the email, mark your calendars. Topic will be dedicated outdoor air systems, which is obviously a trendy topic the past 5-7 years. So it should be a good one. So November 20th. And if you guys are in Illinois and you want to come out to Northwest Indiana, please come join us. We will happily take you. Hell, if you're in Wisconsin and you want to come down, come join us. We'll take you as well. All right, with that, I don't have any more questions pending, so I'm going to go ahead and close the webinar. Like I said, this is recorded, so if you want to have a coworker watch it later, that's totally fine. The recording will be posted up within the hour at the exact same link that you previously registered. If you have any problem finding it, send me a note, and I will get you a link. All right, thank you guys very much. Appreciate it.